Hi everybody. Today we're going to be taking a look at the principles of heat exchange. Now the principles of heat exchange are pretty straightforward. If you have a hot object and it's in contact with a cold object, some amount of heat is going to be transferred. The first principle of heat exchange states that heat energy transfers from hot objects to cold objects. So this hot thing over here is going to have some energy and it's going to transfer over to that cold energy. And what that's going to look like is it's going to look like a decrease in temperature for the hot object. It's going to look like an increase in temperature for the cold object. Now, the exact amount of heat that is transferred is given by this equation here. Q equals mc delta T, where C is the specific heat capacity of whatever subject or whatever object is losing or gaining the heat. Okay. The next principle of heat exchange states, because of conservation of energy, the heat that is lost is equal in size to the heat gained. So what that looks like is it looks like this equation right here. Q gained plus Q lost is equal to 0. This is to say that no energy is gained by the energy that is gained by one of the objects is exactly the same as the energy that is lost from one of those objects. So let's take a look at an example question for this. This question here states a 0.65 kilogram piece of copper is initially at 65 degrees Celsius. This is going to be our hot object for this question. It is placed inside a 1.5 liter beaker of water at 15 degrees Celsius. Determine the final temperature of the copper and the water. So the first thing that we're going to do is we're going to write down our equation for heat transfer. That's going to say that the Q lost plus the Q gained is equal to 0, okay? So the piece of copper is the hotter one, so it's going to be losing some energy, and the water is the colder object, so it's going to be gaining some energy. And what that kind of looks like here is if you have a little beaker over to the side, and it's filled with 1.5 liters of water, you can put in a hot rod of copper, and it's going to put some energy out into the environment or into the water. Now, one of the secrets of heat exchange, or the secret third rule of heat exchange, is that the final temperatures of both of these objects are exactly the same. That is, when the piece of copper cools down, the water is going to heat up, and they're going to do that until they reach the same final temperature. So the final temperature of the copper is going to be equal to the final temperature of the water. Okay, so let's take a look at how much energy is lost and how much energy is gained using our equations of heat exchange. So the Q lost by the water, or by the copper, is going to be given by the equation mass of the copper, specific heat capacity of the copper, multiplied by the change in temperature of the copper. And the energy gained by the water is going to be equal to the mass of the water times the specific heat capacity of the water times the change in temperature of the water. Now this equation is going to get pretty large, but this is the basic idea here. We're going to have to expand this out, and we're going to solve for the final temperature of the copper and the water. Okay. So let's start putting in some numbers here. The mass of the copper is equal to 0.65 kilograms. So we can write that as 0.65 kilograms. And the specific heat capacity of the copper, well, we can come over here to our table and we can look it up. The specific heat capacity of copper is 3.9 times 10 to the 2 joules per kilogram degrees Celsius. So I'll write that down as 390 joules per kilogram degrees Celsius. Now let's take a look at the temperature of the copper here. Well, we know that the change in temperature of the copper is going to be the final temperature minus the initial temperature, which is 65 degrees Celsius. This is all the information regarding the heat lost by the copper piece. Now let's add in the energy that is gained by the water. So if we take a look at the mass of the water, well, we're given 1.5 liters of water. One thing that should be known is that 1.5 liters of water is equal to 1.5 kilograms of water. Now we need the specific heat capacity of water. Let's take a look at our table again, and we find it is 4.2 times 10 to the 3 joules per kilogram degrees Celsius. So let's write that down. I will write that as 4,200 joules per kilogram degrees Celsius. And we're going to multiply that by the change in temperature of the water. Well, the change in temperature of the water is going to be the final temperature minus the initial temperature, which is at 15 degrees Celsius right there. And all of this is going to be equal to 0. Now we want to solve for the final temperature of the copper and water, so we need to isolate this variable right here. Let's simplify our expression by using a calculator to multiply some numbers together here. So first we're going to do 0.65 times 390. If you put that in a calculator, we're going to get that that's equal to 253.5. The kilograms are going to cancel out, and the units will be joules per degree Celsius. And then we'll continue on with our expression as it was before. Then we're going to add on, well, 1.5 times 4,200. That's going to be 6,300 joules per degree Celsius. The kilograms will cancel out. And we're going to multiply that by TF minus the initial temperature of the water. And don't forget, this is all equal to 0. The next thing we're going to do is we're going to expand this once again by multiplying 253 by the final temperature. So let's write this as 253.5. I'm going to ignore the units here, just for simplicity's sake, times temperature final. And then we're going to multiply this by the minus 65 degrees Celsius. If I put this in a calculator, I should get it's going to be 16,477.5 joules. The degrees Celsius are going to cancel out, leaving our final unit as joules here. Then we're going to do the exact same thing over here. We're going to take the 6,300 and multiply it by the final temperature. I'm going to ignore the units, just for simplicity's sake. And finally, we're going to do 6,300 multiplied by minus 15. And we're going to get 94,500 joules. Again, the degrees Celsius are going to cancel out. This will be equal to 0. Now we can combine like terms. I'll keep all the temperatures in red, and I'll keep all of the joules in blue. So we're going to do 253.5 times TF plus 6,300 TF. That's going to combine together to give us 6,553.5 times the final temperature. Then we're going to subtract away 16,477.5 minus 94,500 joules. Combine those together, you should get 110,977.5, and the units are joules. And that's still going to be equal to 0. Now, we can bring over this unit of energy to the right-hand side of the equation, and we should get it rewritten as follows. And then finally, we're going to divide both sides of the equation by 6,553.5. So the final temperature is going to be 110,977.5 divided by 6,553, and you should get an answer of 16.93 degrees Celsius. We're not quite done yet. We need to take into account significant figures. So our initial problem gives us 2 significant figures for the masses and 2 significant figures for the temperature. So our final answer should also have 2 significant figures. So the final temperature is going to be 17 degrees Celsius.